thing for everyone, isn't it? The res that I have on that, no, 1024 by 768. It's not bad, but it's not great. So that's what I'm recording in. All right, well, enough of the fun talk. Let's get to any homework questions. Any homework questions? Yeah. Do I what? I haven't passed it around yet. I'm getting to it. 45, is that what you said? Okay. Let me take a look. I know I sound sick. I'm kind of congested, but I don't think I'm sick. Knock on wood. But so I'm not going to get everyone else sick right here, I don't think. Let's see. So f of x, doing number 45, is negative 5x squared plus 2x minus 3. And is there one in particular you want me to do? The fraction one? Yes? Okay, so what is, we're trying to find f of 1/2. So everywhere we see an x, we replace it with 1/2. So I'll have the negative 5, and then I'll have my 1/2, I'm going to put in parentheses, I'm going to square it, plus 2 times, and then I'm going to multiply 2 times whatever x is, which again is 1/2, and then subtract 3. So there are my halves replacing my x's. Now what is 1/2 squared? Multiplying two fractions, you go straight across, so 1/4, right? Straight across, 1 times 1, 2 times 2, so 1/4. So I have negative 5 times 1/4, and then plus, let's go ahead and do this 2 times 1/2. 2 times 1/2 is 1. You could say 2, it's the same as 2 over 2, 2 over 1 times 1 over 2. So multiply straight across, 2 over 2 is 1. Is that all right? 1. And then minus 3. Now I have to multiply that negative 5 times the 1/4. So I'm going to go negative 5 over 1 times 1 over 4, which would give me what? Negative 5/4, or negative 5 over 4. So I have negative 5 over 4, and then I have 1 minus 3, which is negative 2, isn't it? Okay, so that's where we are right now. We have negative 5 over 4 minus 2. And I can combine these together if I can make them fractions and get common denominators and all that stuff. So I have to turn this into negative 5/4 minus 2 over 1, right? Negative 2 is the same as negative 2 over 1. And now addition and subtraction of fractions, you need the common denominator. We're going to do quite a bit of this today. I need my denominators here to be the same. So I look for an LCD, which is 4, and that means I will have to take the second fraction, the 2 over 1. I will have to multiply the top of it by 4 and the bottom of it by 4. And just that fraction, right? I'm not messing with anything else. Why is it that I'm allowed to do 4 over 4? I mean, why can't I just multiply that by 4 over 4? What is 4 divided by 4? 1. What is anything times 1? Whatever it was, right? So I'm not actually changing the number, I'm just changing the way it looks. And that way it'll have the same denominator as the fraction I'm trying to combine it with. So I have here negative 5/4 minus, multiply straight across on these. 2 times 2 is, 2 times 2. 2 times 4 is 8 over 1 times 4 is 4. And now when we're putting fractions together, if we have the same denominator, right, we just combine the numerators. So I take negative 5 and I subtract 8. What's negative 5 take away 8? Negative 13 over 4. Now that's the way I would accept the answer. The back of the book changes it over to a mixed number. Remember mixed numbers? You say, like, how many times does 4 go into 13? Well, it doesn't, but it goes in 3 times with 1 left over, right? So they say it's negative 3 times with 1 left over, 1/4. Remember mixed numbers? I hate mixed numbers, so I don't care about that. Hate's a strong word. I don't like them. I don't encourage them, okay? Does that help? Anything else? Uh-huh. For which one? For, yeah, but what plugging in what? Oh, plugging in the 0.2. Okay, so we're given a function, g of x equals 4x cubed minus x plus 4, and I want to find g of 0.2. So that equals 4 times, now I'm going to plug in 0.2, and it gets cubed, minus, now I plug in the 0.2 for x, and then plus 4. So I need to figure out what 0.2 cubed is. And if you don't know what 0.2 cubed is, that's okay. You just need your calculator. You need to go 0.2 times 0.2 times 0.2. What do you get? 0.008. So 0.008 minus 0.2 plus 4. Now on your calculator, what is 4 times 0.008? 0.032. Then the next one is minus 0.2 plus 4. And then just do all that on your calculator. 0.032 minus 0.2 plus 4. What do you get? 3.32? 832? 3.832. You would, right? Okay, here's the 0.2 plus 0.2 plus 0.2 would be 0.8. See, think about it this way. Take a number that's a little easier to work with. If you take 0.1, let's say. 0.1 is 1/10. That's what 0.1 is. Remember when we were learning decimal positions? First position is tenths, hundredths, thousandths. Remember that? Okay, so 0.1 is 1/10. If I do that cubed, that's a tenth times a tenth times a tenth. And what happens is across the top you get 111 multiplied, that's 1. Bottom 10 times 10 times 10, that's 1,000. So you get 1/1000th, which turns out to be 0.001. So it's just the fact that if you take a number that's smaller than 1 and multiply it times another number that's smaller than 1, the number actually gets even smaller. So 0.1 times itself 3 times becomes 1/1000th. Zero one, yes, it would go one more on that one. Yeah. Okay, let's get going on today's stuff. We're going to jump to chapter 5. And in my 9:30 class, I thought I was going to get through 2 sections today, but we kind of got to a point where we decided not to. And we ended class. We didn't end class early, but there was time at the end for everyone to take do like a quiz. So my plan is to go through this material, and then at the end, the last 15 minutes, give you maybe a 2-question quiz, and you'll be allowed to use your notes in your book, but you won't be able to help each other. And it will cover what I'm covering today. So if you have any questions, make sure you ask. All right, we're going to start off 5.3. This is called Intro to Polynomials and specifically adding and subtracting polynomials. Okay, so what I'm going to do is I'm going to start this out. There's going to be a couple of definitions today. I'm going to give you a word, and I'm going to define it, and I'm going to show you some examples, and we're going to have several of those today. So we need to make sure that we're all on the same page when I say, when I say you have to do this, and I'm talking about words, and you're like, what is that? You need to know what they mean. So first term today that we're going to learn, or first definition, is something called a term. What is a term? All right, so what I will do is I will first show you some examples of what terms are, and then we'll kind of talk about what the property is to be a term. So here's some examples. First one. The number 4 by itself is a term. All right? I'm going to separate it with a comma. Here's the next example. 4x is also a term. 4x squared is a term. 4xy is a term. 4x squared y to the 5th is a term. And I could keep going. 4x to the 3rd y z to the 7th. These are all terms. So what makes a term is that first, you don't have any addition or subtraction, right? The only operation that you see anywhere in these examples is what? What's the implied operation? Multiplication, right? Now, 4 by itself is just 4, but 4x means 4 times x, right? This means 4 times x, right? X squared really means x times x. This means 4 times x times y. 4 times x times x times y times y times y times y times y. I mean, we don't write it y. We just write y to the 5th. But everything here is implied multiplication. So all a term is a mixture of numbers and letters and multiplication between those. That's a term. All right, so that's what I'll write here. A term has number and variables with implied multiplication. Now, within every term, there's something else in a term that we need to know, and we need to know what it's called. And that is simply the number that appears in the term. In this case, every single term that I gave you up here has the same number in it, right? 4. That number is called the coefficient of the term. So that was my next kind of definition. The coefficient of the term is basically the number in front, right? The number out front. And I'm going to also say here, it might be 1, or it could be -1. So it might be 1 or -1. Just be careful. So I'm going to give you another example. And you tell me these two things. Is it a term? If it is, what's its leading coefficient? Or what's its coefficient, sorry. Is that a term? Yes. And what's the coefficient of this? 5, right? If I have this one right here, -2x, that's a term? Coefficient, -2, right? We'll do another one over here on the side. How about -z? Yes? What's the coefficient? -1. So I don't write the 1, right? But the negative sitting in front implies that there's a -1. Okay? Now that's going to become important for what we're going to do now. All right? One more example. 3/4 xy squared. Is that a term? Yes. Now, I said that you have to have variables and numbers being multiplied, right? You might say, well, 3/4 is division, but if you remember when you learned division, division is multiplication. It's just multiplication of a reciprocal. So division is still technically multiplication. So this is still a term. It's this times this times this. So we still have a term, but the coefficient now, unfortunately for us, is a fraction, right? 3/4 would be the coefficient. All right, I know this is exciting, but it's going to get better. Now we talk about what are called like terms. Like terms. Like terms are terms that have some properties, some characteristics that are similar. Kind of like, you have, anyone watch the that dog thing that happens once a year? What's that thing? It just happened in, I think it was in New York, the dog show. Puppy Bowl? I don't know. No, the one where they have the dogs that are all, and you got some idiot running it around. You know what I'm talking about? What is that called? Yes, it's something like the AKC, whatever, Top Dog. I saw it on the news. I don't watch it. I just saw it on the news. Anyways, they categorize the dogs in their breeds, right? So like you have the certain breed or certain, working class dogs versus, well, that's what they mean. What I mean here by like terms is there's some terms that they're not completely different. They have very similar characteristics, so they're like. And what happens is that if you have like terms, you can combine them together. You can add them and subtract them. But if they're not like, you can't. So we have to understand what it means to be like first. And so here's what it takes. For two terms to be like, they must have the same variables. Okay? They must have the same variables. And then also same powers or exponents on variables. That's what it will take for us to say two terms are like. So I'd like for you to look up at the example we had above, where I'd given you 4 different terms, right? Are any of those terms like terms? Well, let's start with the first one, 5xy. Do any of the others have an x? Yes, the bottom 2 have x, right? But the one that I circled also has a y. Do the bottom 2 have an x and a y? Well, that left one doesn't. This one does, though, right? But are the powers exactly the same? No, the x's, right? The x is just x, but the one I circled has y, the other one has y squared. Because the other one is y squared, they're not like. I mean, it has to be dead on exactly. Variable for variable, power for power. Make sense? So none of those are like terms. Well, you can check. None of them, the top right, z, none of them have z, so you can say nothing's like to that. This one has x, that one has xy, that's too much, right? This one would have to have a y also. And then this one has the y squared, so you can see nothing matches, no like terms. So let's look at some things that are like terms then. Some examples. How about -5x, comma is the one I want to compare it to, 4x, right? Those are like terms. They both have x. What's the power on that x? 1, right? It's not there, but there's a power of 1. Now, what we don't look at, I don't know if you've noticed this, what we aren't looking at is the what? the coefficient, right? We don't care. To be like terms, we don't care about the coefficient. We don't care about the number. We just care about variables and powers. How about this? So look at them. Are they terms? By themselves, are they terms? Right? They're both terms, right? I brought my laser today. I just thought it might be fun. Right? This one right here on the left has multiplication between all those. That's a term. This one, multiplication. Okay, this one has an x. This one has an x. They're both to the first power, aren't they? All right, this one has y squared. This one has y squared. They match. X's for x's, y's for y's. Now, the fact that the order is different, does that matter? Well, multiplication is what we call commutative, meaning that you can always change the order of multiplication and it's still the same. So that's okay that the order is different as long as the variable appears and the power is the same on each of them. So these are both like terms. How about this? 9 and -3. So let's before you say yes or no, let's think about this. I was talking about the dogs, right? Like terms, like dogs, like animals, you could almost say. You know, you have maybe that's too much of a stretch. I won't go there. I'm talking about trying to breed different types of animals, but I'm just not even going to go there. The big question is, can you put these two together? Like, do you have a way of combining those? If I asked you to add or subtract them, could you? Yes. Because they're just numbers, right? So what you could do to convince yourself that these are like terms is just throw something on the end of this. How about this has an x, this has an x to the 0, 0. Do you agree that those both are the same? Look, what's x to the 0? 1. What's x to the 0? 1. So really, there is an x to the 0 sitting next to it. But there's also a y to the 0 and a z to the 0 and a bunch of other crap, anything you could think of. So when it really comes down to it, if it's just a number, they're both numbers, they are like terms. So now that we kind of have an idea, I hope, of what terms are, what coefficients of terms are, and what it takes to be like terms, now we talk about what it takes to add or subtract terms together. Okay, adding and subtracting like terms. Like terms. Okay, the first thing, make sure they are like. Second thing, add or subtract coefficients. And I'll put a note under that. Don't change powers. That's just a reminder. When we are adding or subtracting like terms, you never mess with their powers. All you ever change is the number in front. That's it. That's all that will ever change is the coefficient. So here are some examples. We'll start off with something that most people would be comfortable with. What if I said take 5x and add it to 3x? Most people would be comfortable with that being 8x. Well, what we're really doing is we're saying these are like terms, right? We have two terms, term 3x, term 5x. We have them being added together. They are like terms. They both have x. The x is raised to the first power. And therefore, to add them together, all we do is we look at 5 and we look at 3. We add 5 to 3 and we get 8, right? And we do not change the variable at all. We just put x. So we don't make that 8x squared, right? It's 8x. How about negative 4xy plus 7xy minus 3x squared? This is another example. How many terms do we have? Total of 3 terms, right? Total of 3 terms. I'll go old school. I'll put the laser down and go old school style now. 1, 2, 3, right? Are they like terms? 2 of them are. The third isn't, right? The first 2 are like terms because they both have xy. The third one is not because it has x squared, and it's missing a y. So the only 2 that we can combine together are these 2. So all we have to do is identify the coefficients on each one, right? Negative 4 and positive 7. So what's negative 4 plus 7? 3. So 3, and then I won't change the variables, so 3xy, and then I still have over there minus 3x squared. That's it. That's all we can do, okay? We don't want to try and do any weird voodoo magic on that and try and do math that's not legal. That's it. That's all we can do. So we kind of also have to know when to stop. Like, when is it that we can't proceed with anything here? What would happen if I did something crazy like this? 5x cubed minus 3x plus 7 in parentheses minus 4x cubed minus x squared plus x minus 10 in parentheses. Now this is starting to look like a mess, huh? How many terms are in the first set of parentheses? 3. In the second set? 4. In the first set of parentheses, right, order of operations says do what's in there first. But can you put any of these together? No, none of them are like terms, so we can't. How about in the second set of parentheses? Can you put anything together here? No, none of them are like terms either, right? So if we can't do anything in the parentheses, then the next thing is to step outside parentheses and do whatever's out there, or get rid of the parentheses. So in order for me to drop parentheses, I always must distribute through with the number that's in front. So on the first parentheses, what number is sitting out front out there? A positive 1, right? Positive 1. If there's nothing there, it's a positive 1. So distribute a 1 through. Doesn't that just leave everything the same? Okay, so it becomes 5x cubed minus 3x plus 7. But now in the second parentheses, we have a minus. So that's like a negative 1, and that must go through. What does a negative 1 really do to all the terms in here? Changes the sign, right? So if this was positive 4, it becomes negative 4. This is a negative, really like a negative 1, it's going to become a plus. And then this plus becomes minus, and that minus becomes plus. So we get negative 4x cubed plus x squared minus x plus 10. Now we've got this big string of, 7 terms. And now we see if there's any like terms now. And I see x cubed here, x cubed here. So I can look at their coefficients, 5 and negative 4. So I just do 5. I take away 4, right? 5 minus 4 is 1. But then I have to keep the x to the third, don't I? So it'll just be 1x to the third. I don't need the 1, but I'm going to write it. You could just write x to the third. Now, what else? Do we have any other like terms? The negative 3x here, and then the minus x here, right? X squared doesn't look like it has any others to join with, does it? We'll still bring it with us, but we're just not going to be able to combine it. Now, what the book likes and what we like to do in math is we like to put all our answers in what's called descending order, which means we like to make it be the highest power that we see and then come down as we go. But I'll do that on the next step. I heard someone say we had the x's, so let's go after the x's right now. We had the x, the number in front was -3 here. The number in front was what here? -1. What's -3 take away 1? -4. So it'll become -4x, right? The x doesn't change. And do we have anything else we can combine together? 10 and 7, right? Those are just numbers. So 10, add 7 to 10, and you get 17. And now we'll bring that x squared, that poor guy that didn't have any friends, just comes on down, right? Now I will put it in descending order, meaning highest power of x, and then decrease it until you get to the number by itself. Y'all see what I mean by that? So x cubed, then x squared, then x, then no x's at all. Now I won't take off on a test if you don't put it in descending order, but you should do it. It's useful later. So far, what do y'all think? It's all right? Yes. No. You mean like put the 5x cubed and put this right here underneath it? Well, how did you get plus x, though? Are you talking about you looked at it way up here and did that, or you did it? Ah, I see what you're saying. Okay. You can do that, but I think this is, I'll squeeze it in here so I can address that. Okay, what you're saying is instead of doing what I did, take the 5x, since you're subtracting that whole thing over there, right? You put it under here, 4x cubed minus, well, you put plus x there, right? And then you put the minus 10 under the 7. And where'd you put the x squared? You just stacked it out here. And then you did this, and then came down. If you're going to subtract that way, when you subtract, everything changes. All the signs change. Okay? Because what you're doing is you're subtracting the whole thing. So I take the 5x cubed, I subtract this one, that gives me the x cubed. -3x, I subtract a positive x, becomes -4x. 7, I subtract a -10, becomes plus 10. So you can do that as long as, again, you still have to change the signs. All right. Moving along. How about this? 3/4 x squared minus 1/2 x plus 5/7 minus 1/3 x squared plus 1/2 minus 3/8 x. You wanted fractions. I'm here to provide those for you. Now, one thing I will point out is that on our last test, whenever we saw fractions, didn't we do like LCD and multiply both sides and clear fractions? Do you remember that? It was one of our steps. We cannot do that here. And the reason why is because for us to do that clearing of fractions, we had to have an equation. That's what we had been working with, equations. This is no longer an equation. This is called an expression. There is no equal sign in there. So the only thing we can ever do is get common denominators and combine together, but no LCD canceling things out. So first things first. In the first set of parentheses, we have 1, 2, 3 terms. Second set of parentheses, 1, 2, 3 terms. in the first set of parentheses is anything like? Nope. Second set? Nope. Okay, so let's get rid of parentheses. On the first one, should just be able to drop it, but on the second one, I must pass that negative sign through. So your next line should look like this. 3/4 x squared minus 1/2 x plus 5/7 minus 1/3 x squared plus or minus the next one. Minus 1/2 and then plus 3/8 x. Now I will start to combine like terms if possible. I've got an x squared here. I've got an x squared here. That's the only ones I have, right? On your homework, you might have problem where you actually have 3 of them have x squareds. Then you have to combine all 3 numbers together, all 3 coefficients. So I'm going to put 3/4 together with what? Negative 1/3. Right? So I've got to do that. Up to this point, it's just been integers. We just add them up. We've been doing them mentally, right? Now we have to actually make sure we can put these fractions together. So it's time to talk about fractions. 3/4, I'm subtracting 1/3. How do you, this is almost like a rhetorical question, you're asking yourself, how do I do that? Everyone has learned different ways of doing it. I don't care which way you do it as long as it's right, but I will show you 2 different ways of doing it, all right? One way is to find the LCD, which in this case would be what? 12. And what you want to do is you want to make both denominators 12s. So you isolate all your attention onto the 3/4 and you say, okay, make that 4/12. How do I make that 4/12? Multiply by 3. But whatever I do on the bottom, I have to do on top. So I'm really coming in and multiplying by 3/3 right there. And then on the other one, I have to do the same thing to make the bottom a 12. But here I'll have to multiply top and bottom by what instead? 4 and 4. 4, 4. Now, figure out what you get with each of these multiplications. First one, 9/12. Second one, 4/12. It's just multiplying straight across. So this is equal to 9/12 minus 4/12. And once you do that, 5/12. So all you do now is 9 minus 4. That gives you 5. 5 divided by 12. Okay, that's one option. How many of you have seen that, are comfortable with that, ready to go with that? Okay, if that's what you're good with, then so be it. Here is another option, though. Sometimes I'm a little bit weary about adding this in there. Yeah, I don't even know if I should. I'm kind of like on the fence about this one. Let's see if anyone has seen it. If you have 2 fractions and you're adding or subtracting together, instead of doing all LCD and all this stuff, what you can do is, it's not technically called cross multiplication, but it looks like it. You start bottom right corner, you multiply up to the top left corner. What's 3 times 3? 9. Okay, so I went from the bottom to the top left, right? So I went like this. Okay, so that's going to be 9. Top left corner of my answer is now 9. Now, do this way to this way. So 4 times 1 is what? 4, and that goes in the top right. And what was the operation between the 2? Subtraction. So I put a minus sign between them. And then I divide that by whatever I get when I multiply across the bottom. Multiply straight across the bottom and you get what? 12. And that's 5/12. Now, the reason I don't like that is because it doesn't, you don't really know why it works. It just kind of works. And there's another reason why I don't like it. This can create huge fractions, because if your denominators, I'll give you an example of something. If I had like 1/12 plus 9, well, no, let's go 19/24, something like that. Check this out. If you were doing it the way we all had done it up here, All you'd have to do is get an LCD of what? 24. So you multiply top and bottom here by 2, wouldn't you? And you'd get what? 2 over 24 plus 19 over 24, and put together it's 21 over 24. See how quick and nice that was? But if you do it the way I just showed you, you have to do what? 24 times 1, which is 24. And then multiply this way, 12 times 19, which is 228. So plus 228 all over 12 times 24, which is 288. 288. So then when you put those together, you get what, like 252 over 288. And that fraction reduces to become this. But you don't see it right away, do you? Do you see what I mean, though? This can create very large fractions, but what I can promise you is that this is right. It's just not reduced completely. So there are pros and cons to both ways. I think this is the way you should know how to do it, right here. Okay? No, there's not. All you do is you start with things that you know go in there, like 2, right? They're both even numbers, so you can start with 2. And reduce that, and then just keep going until, yeah. Yeah. There's actually something, let's finish the problem, then I'll tell you this little story, if y'all want to hear it. I mean, I don't want to bore you guys. I know y'all want to do this more than you want to hear random stories. So what else like terms-wise? And I need to come back and highlight, what was I going to have here? I put that 3/4 together with the minus 1/3, and we got 5/12, right? That'll be in front of our x squared. Let's just remember that, because I'm going to need it. Now, our other like terms, how about x's? I have negative 1/2, right, and plus 3/8. Make sure that you grab the sign of the coefficient, right? The coefficient is not just the number, it's the number with the sign. So it's negative 1/2, and over here it's positive 3/8. Here's what I want to do. So what should I do to get an LCD? Times 4, the first one, right? First one, 4 on top, 4 on bottom. So do that multiplication, 4 top, 4 bottom. Negative 4 over 8. Be careful with that. It's negative 4 over 8. And then the other one is plus 3/8. Add across, negative 1 over 8. So that will go in front of x, right? Finally, the last things to put together, positive 5/7 minus 1/2. Positive 5/7 minus 1/2. What's an LCD here? 14. So 2 on top, bottom on the left one, 7 top, bottom on the other one. Now, I'm going to do my shortcut. It's 10 minus 7 is 3 over 14, which will give you the same. That's what everyone else got, right? 3 over 14. So, I mean, I'm not saying I don't like the way that I showed you with that cross thing. It's just that that shouldn't be your only method. You should be able to do both. See how that one works a lot quicker that way, especially if you have the idea in your head. Just do that and that. Okay, so here's my final answer. My final answer is 5/12 x squared minus 1/8 x plus 3 over 14. Okay. Do y'all want to hear this story or not? Yeah. That only sounds like a few people saying yes. Do y'all want to hear a story or not? Oh, okay. I'll spare us. This is actually, real stuff here. when you send something like email, or like when anyone has their website, like on their bank information and stuff, you go to a website, right? And you go to these things and it's secured, right? The way that things are secured by financial institutions is using something called RSA encryption. Now, RSA encryption, these letters are the letters of the last names of the guys who came up with this encryption. Now, I don't want to go through this whole story of what encryption is, but it's a very simple idea. I'm trying to get a message to you, right? But let's say that I can't physically get to you. So the only way I can give you this message, like there's no class on Tuesday, right? If I only want you to know, if I yell it out, everyone else knows, right? If I write it down, pass it to them, maybe someone will intercept it. So for as long as human beings have been alive, we've been trying to send messages to each other without other people getting their hands on it, right? So it's been this battle back and forth for thousands of years, how to send messages without other people being able to interpret them. Does that make sense? Encryption is basically me somehow sending a message so that even if someone gets it, they wouldn't be able to read it because it would be somehow mixed up in letters and numbers and they wouldn't understand it. So one of the most basic forms of encryption is to create an alphabet with numbers, right? E, what, F, G, H, I. So let's say that I want to send the message 89. So I send you this message 89, right? And someone picks it up and they're like, what was he saying to him? 89. What's 89? Well, what is 89 according to this key? Hi, right? So for every letter I assign a number to it. This is called basically an alphabetic code. And it's stupid because you can break this pretty easily, right? So then it becomes more complicated. And what you do is you do something like you have two keys. So maybe you have that A, B, C, D like that, and then you have another A, B, C, D, and now maybe you start at 2, 3, 4, 5. And so the first letter, 8, comes off of this key, and the second letter, 9, comes off the other key. And so in order to break the code, you have to have both keys. And then maybe you have multiple, this is called polyalphabetic codes. So the thing is, you can get more complicated with your coding, right? Like how you're gonna encrypt the message. So you have the people encrypting, who are the people who are trying to hide it. Then you have the code breakers, the people who are trying to break the code. And for thousands of years, it's been back and forth, back and forth. Sometimes the people who are encrypting have the upper hand, then the code breakers find this way of figuring it out, back and forth, until RSA encryption came. When RSA encryption came, it's been pretty much determined that that way of coding something is pretty much impossible to be broken. It hasn't been broken, and if you could break it, you would either, like if you went home tonight and you found out a way of breaking RSA encryption, you would either be dead tomorrow, missing tomorrow, or you would be like, you're probably dead or missing, okay? Because no one's going to pay you for it because you'll bring the entire world to its knees because you will have a way of breaking all code. You know what I'm saying? So you'd probably just go missing. No one would ever see you again. But it's one of the math questions, one of those big math questions that if someone could figure it out, they'd be in business. So let me show you what it is. It's not complicated. You'll probably look at it and be like, are you serious? That's all it is? I'm not going to break it. There's no way I could break it. Okay, here's the way it works. Let's take the number 15. Okay? Does everyone know that that number is made up of two other numbers? Okay? Would you agree that it's made up of the two numbers 3 and 5? 3 and 5 are what we call prime numbers. Prime numbers are numbers that are only divisible by themselves in 1. Y'all heard that before? Like the number 9 is not prime, right? Because 3 goes into it, 1 goes into it, 9 goes in. So primes are numbers that are only divisible by themselves in 1. So the first couple of primes are 1, 2, 3, 5, 7, 11, 13, and then the list keeps going, right? Turns out there's an infinite number of primes. These primes go forever. Okay, so back to this. 15 comes from 3 and 5, right? So when I'm going to send somebody a message, like you, a message, and I'm not going to be able to explain all the details of this. What happens is that you will send, what's your name again? Alex? Okay, Alex would tell me, hey, and he's telling to everyone. Everyone can hear him. He's saying 15, okay? And so I'm saying, all right, 15. So I write my code. Whatever I want to send to him, I write it. And then I use that number 15 in some way to scramble my letters around, okay? That's the part I'm not going to get into. But it's a way of mixing the letters. So 15, right, mixes it. And now I send it to him. And anybody who wants it can grab it. But the only way that they can break it is if they know that 15 comes from 3 and 5. Y'all still with me? Okay. That's 15. That's stupid. The way that they do RSA encryption is whoever wants to, you want to come up, Alex wants to come up with his number 15 that he's going to tell everyone. What he does is he goes and he gets a prime number off this list, a prime number that's 40 digits long. Okay? 40 digits long. And he takes another prime number that's at least 40 digits long. He multiplies the two together, so he gets an 80-digit number. And that's the number he tells everyone. That's my number. So I get my thing. I mix it using his number. I send it to him. Everyone knows the 80-digit number, but nobody can figure out the two 40s it came from except him. So that sounds like, well, you could just have a computer do it, right? Just put the 80-digit number into a computer and have the computer try and figure out what two numbers it came from, right? Seems like a computer would be able to do it. Well, the way that I said 40-digit numbers, right? The reason you choose 40 digits is because the guys who came up with this realized that the longer the digits, the more time it would take a computer to try and figure it out, right? So they said, well, should we use 2-digit numbers? Hell no, man. Anyone's going to be able to break that down. Should we use 3 digits? No. 4? How much? So they said 40, and here's the reasoning. They said, look, if we take every computer on the planet, every computer, and we all try and get all those computers to try and attack that problem, his 80-digit number, it should take 10 times the age of the universe. That's the standard for that RSA encryption. So if computers get faster, they just take bigger numbers, and bigger numbers and bigger numbers. So right now, there's no easy, efficient way for someone to give you an 80-digit number and you be able to come up with the two prime numbers it came from. There's no way to do it easily. Yes? Yeah. What? Let's talk about it afterward. I have heard a little bit about that. But that's the standard. That's the RSA. That's RSA encryption. That's the standard they use. So it's a very simple idea. You start with a composite number and you try to come up with the two primes it came from. If you can figure that out for an 80-digit number, then I'll never see you again. Why? I don't know why I thought of that. What was I thinking about that up here? I apologize. I got kind of off. Where was it? It's always something that sparks something like that in my head. It's just one of those glitches. Yeah, maybe that's what it was. I don't know. I just wouldn't shut up, and that was it. Well, I've always been fascinated by the code breaking stuff. If anyone's ever done or heard of the Enigma, y'all ever heard of the Enigma machine? It was a machine the Germans used. The Germans used a machine called the Enigma, and that's how they coded all everything they sent back and forth to each other. And for the longest time, we could not figure out what the Germans were trying to do because everything was coded with this machine called the Enigma. And it wasn't until we actually captured one of the machines that we were able to break the code because we had the friggin' machine in our hand. So we were able to figure it all out. And then they changed the gears a few months later because they figured out that we knew exactly where they were going to be all the time. And so, but it was too late. At that point, we had already turned the tide of the war, and it was kind of over. But the Germans were big time on code. I mean, they could really decipher really well. So when you hear that phrase, like it's an enigma, that term comes from the idea of the enigma is like the impossible. You just can't break it. Okay, let's try another one. Sorry. Let's get back to this. Yeah, let's sign in. Thank you, Alex. I'll give you something for being my participant today, my volunteer code guy, code breaker. Yeah. All right, here we go. Let's do one with decimals because I know you like decimals. 0.15x cubed minus 3.2x squared plus 5.7 minus 2.13x squared minus 4.2x minus 0.031. Now notice I did not put zeros in front of my decimals. You can or cannot do that. It's up to you. Now, do we have like terms? We do have like terms, but they're not in the same parentheses, right? In the first parentheses, none of those are like. Second parentheses, none of those are like. So the only way to get things together here is to get rid of those parentheses. So we'll have to distribute a negative sign through the second one. Y'all agree with that? Did I change all the signs properly here? Yeah. Everything that positive became a negative, that negative became a positive, that negative became positive. Now let's try and collect like terms. Now be careful here. X cubed. Do you have any other x cubes? You do not. So that one's not going to go with any of the others. X squared, though, you have two of them. So what I need to do now is I need to combine negative 3.2 with negative 2.13. Negative 3.2 minus 2.13. Now you can use your calculator here, but you got to make sure you type this in properly. What is that going to be? Negative 5.33. Negative 5.33. So here's what I'm going to put. I'm going to put the 0.15x cubed. I haven't messed with that. This became negative 5.33x squared. The x terms, do I only have one x term? Oh, okay, cool. All right, but we still have to put together the 5.7 and the 0.31. Yes. So anyone else need to sign in? Thank you. Anyone else need to sign in? What is the 5.7 and the 0.31? What is it? 6.01. So if you have any questions on how we got this, we're going to need to work together on your calculator to make sure you understand how to use your calculator for this. All right? And that's it. We're there. All right, let me give you what I'd like for you to do as a quiz and for homework. Yeah, I would like for you to do this as a quiz. We have 10 minutes. See if you can finish these two in 10 minutes. I'm going to stop recording. So, uh-oh.